Good morning, students. Today we shall start the next topic, that is small signal BJT amplifier. You remember, before this we have learned what is biasing, why at all we need to do biasing. We have learned various methods of biasing. And of course, in that we said that the self-biasing or potential divider biasing is the most popular. Then we learned what are the conditions, how the bias point, that means value of ICQ, changes due to temperature and other parameters of the BJT. Then we have learned what are the various techniques to circumvent or minimize those bad effects of bias instability. After all this, we are now more or less ready to learn what is a small signal BJT amplifier. Now, you will ask why this word small signal. That is because the amplifiers that we are going to study now are for small signal inputs, some millivolts, of the order of 100 millivolts or less, because you heard the diode characteristics, the nonlinear characteristics. And transistor's base emitter junction is actually a PN junction, so its characteristics is nonlinear. We keep the signal value very small so that within the diode characteristics, whatever the small range it occupies, the characteristics can be considered linear. And that is why we call it small signal BJT amplifier. If your input is very large, then amplifier design would be something else. Now, two things. This was the biasing circuit, that we learned, and we go to the zoom in condition. This biasing circuit that we learned, and RB VBB was the Thevenin equivalent of your potential divider, where RB was equal to parallel of R1 and R2, and VBB is the potential created by the potential divider here. And this was the IC VC axis in DC. We are still talking about DC. And this is the red line, is the load line, whose equation is VCC equal to IC plus RC plus this potential here VCE, right? From here we get IC is equal to minus 1 upon RC VCE plus VCC by RC. This line is called the load line. This is a straight line. And he said that in various operating conditions, IC and VC may have different values, but that coordinate must always lie on this straight line. The slope of this line is minus 1 upon RC. So when collector current IC is 0, the across the collector emitter of the transistor is equal to VCC. That means voltage appears here. And when VCE is 0, then full potential appears here. So this current is equal to VCC by RC. These were transistor characteristics, transistor output characteristics, you remember. And you are the transistor output characteristics. And you remember from your device classes that as IB increases, that means base current increases, the characteristics jumps from one to other characteristics. For any particular IB, let's say IBQ, This is the characteristics, and this characteristics gives the value of IC and VCE. So, of course, there are two conditions between IC and VC. One is this characteristics line, and there is this load line. So, actual operating conditions must intersect each other, and this intersection point VCEQ is the bias VCEQ here, and this current ICQ is the bias current here. Bias means the DC condition when there is no signal. And once there is a signal, then what happens? There is a, over and above the DC current IB, there is an alternating current here that keeps on changing the VCQ, and that keeps on changing the IC values, and output RCIC keeps on changing like this. This was one lesson that we have learned. Next lesson that also we have learned, that provide bias stability, a resistor RE should be connected at the, and we have learned this relation between RB and RE, that RB should be equal to or less than beta RE by 10. With these lessons, two lessons we have already learned. Next we go to slip over to the next point. Here, also we have learned the self-biasing technique. This is the self-biasing point circuit. This was the equivalent of this parallel series combination potential divider. And from here we found, you remember from your note, the value of RB is equal to R1, R2 divided by R1 plus R2. That means this RB, in this equivalent resistance RB, is these two resistors in parallel. And VB, that means potential here, VBB, is of course equal to VCC divided by R1 plus R2 multiplied by R2, that is the potential here. Also, there was another equation that we have learned. If you go to the base emitter loop, then VBB is equal to IBRB, this current IBQ into RB, plus this potential barrier VBE, plus this current RE-IEQ. So if we take VB to the left-hand side, then VBB minus VBE, this IBQ actually ICQ by beta RB, and this IEQ is approximately equal to 99.9% equal to ICQ. So these two together now means ICQ by beta RB plus beta RE. So from here we get ICQ is equal to multiplied by this VBB minus VBE divided by RB plus beta RE. All this we have already covered. Next, with this much knowledge, we can now proceed to small signal BJT amplifier. This is the BJT amplifier. We start discussing new things. For designing, let us first, you have to select the BJT, that is a transistor that we want to use. If you go to the transistor manual, which you have in the laboratories of your own engineering college or institute, you go to the transistor manual, you will find thousands of different types of BJTs, and their applications are different. You can ask your teacher which BJT you should start with. Start with some simple, easily available audio BJT. And BC547 is, for example, is one of such very common BJT which is available everywhere. Cost in the market is also not more than 20 rupees a piece. Now, then you go to the BJT 547 characteristics, or nowadays you can even get it through Google search. It is given that maximum current through this BJT is 100 milliamps. Is given 100 to some value. Maximum power handling capacity is 500 milliwatt, and VBE, that's best emitter junction voltage, is 0.75 volt. Mind it, these values changes from transistor, a piece of transistor to another piece of transistor. You can always measure it. Now DC load line. What is the DC load line now? This Kirchhoff's KVL equation is VCC equal to ICRC plus VC, this potential, plus IERE. Right? Now, IE and IC, as I said, they are almost same. So it is approximately VC plus IC into RC plus RE. So now this DC load line has a slope of 1 upon minus 1 upon RC plus RE. So this point is here and this point is here. This is the red line, is the DC load line. You can see from this equation, when VC is equal to 0, then IC is equal to VCC divided by RC plus RE. That means this point. And when IC is equal to 0, then VC is equal to VCC. That means this. Apparently, what is this Q point? We discussed earlier. Q point should be at the middle of this DC load line. Right? Should be at middle of the DC load line. Right? That case, VCQ, you can ignore these calculations. In that case, VCQ point is half of VCC. This is VCC. It is half of VCC. And IC is given by this equation is VCC divided by RC plus RE, because the slope of this line is minus 1 upon RC plus RE. So this is the quiescent point. When you design the transistor amplifier, the ICQ, you provide the bias in such a way that means VBB, etc., that we discussed in our last slide. You design those points such a way that ICQ becomes VCC divided by RC plus RE. VCC you know, RC RE also you have selected. Now, but here there is a but. What is this but? Original diagram from the last slide. But signal component is superimposed. When this signal component is superimposed, then actually I see there is when signal component is superimposed, then this VO, output voltage, will be the DC voltage, VO, capital VO, plus AC voltage. AC normally we signify by small v, right? Will be equal to VCC minus DC current IC plus AC current IC into RC, right? So, signal output V. What is the signal output? VO is ICRC. Value of IC would be higher. This is the signal output, which is IC multiplied by RC. So, it will be higher if IC is higher. But because of this resistance here, I see this current through this line is little less. Right? You remember, biasing this resistor was not there. But for bias stability, you put in this resistance. But this resistance decreases the value of this current a little bit. And since it decreases the current a little bit, the output VO also decreases a little bit. That means the amplifier gain drops a little bit. So this drop could be eliminated if this resistance is short circuited. Short circuit this, then bias instability cannot be taken care of. So what do? We use an emitter bypass capacitor, this capacitor. Short circuit RE at the baseband frequency, right? Now, this is a signal amplifier. Let us say you use an audio amplifier. Audio frequency is normally ranges from 500 to 600 hertz up to maybe 5 kilohertz. And normally we test all audio amplifiers at 1 kilohertz. So in this frequency range, set this capacitor in such a way that in this capacitor impedance is very, very small with respect to RE. Right? So, which will short circuit RE in baseband frequency. But so far as the DC quiescent current is concerned, capacitor is open circuit. So, DC quiescent point or ICQ does not change. You got the technique? I repeat once again. We put this capacitor in such a value, we choose the capacitor in such a value that during the range of our operating frequency, its impedance is much, much lower than this emitter resistance RE. So, this loss of output RE is compensated, then this loss amplifier gain will increase. But so far as the DC current is concerned, this capacitor is open circuit, so ICQ does not change, right? Use this technique, then you are putting yourself in a different type of a problem. Now in the in the collector emitter path, that means this collector emitter path, resistance RC plus RE for the DC current, but only resistance RC for the AC current. So I have two types of resistances. RDC, we call it RC plus RE, and RAC, we call it RC. So we shall have two different load line equations. So far we had only one DC load line. Now for AC, it is not the same load line, it's a different load line. The DC load line slope is this slope, this DC load line. This we have done earlier, is minus 1 upon RC plus RE. But AC load line slope is minus 1 upon RC. This is the slope. Blue line is the AC load line slope. Now, how do we tackle both of these load lines together? Now, if the Q point is still in the middle of this DC load line, the red load line, it is longer above the Q point and shorter below the Q point. So, if my Q point is still here, then I can have only this much of a signal swing at the output. The upper part is unused. So I cannot have maximum AC swing at the output. If point is still in the middle of the DC load line. So actually, the Q point now should be in the middle of the AC load line, like here, right? So this will be the new value of VCEQ and ICQ, which is in the middle of the AC load line, but a little higher on the DC load line. Then I can have this full swing at the output. So my design approach, this will be my design approach. that quiescent point will be not in the middle of the DC load line, but in the middle of the AC load line. And the calculation approach we shall, of course, discuss. Now, what are the coordinates of this new Q point? Point is such that this is the DC load line on which another AC load line of slope minus 1 by RC, they intersect each other. And there has to be an intersection point because AC load or only the AC output. And AC output can reduce, AC output can reduce, it can still reduce, and sometimes AC output can be zero. If you remove the signal input, then signal output is zero. And when signal output is zero, then you are left with only the DC current. So the Q point has to be on the DC load line, but in the middle of the AC load. That is the trick. I repeat once again. Q, that means the DC load line and AC load line must intersect at the Q point, and Q point will be on the DC, will be on both AC load line and DC load line, and we find Q point, if you select a Q point at the middle of the AC load line, it becomes a little higher than the middle of the DC load line, because this was a lower and this is higher, and then you can have the full output swing. Now we have to find out the value of this VCQ ICQ by equating the two equations of DC load line and AC load line. Let's see how we do it. This is the picture from the last page. How we do it? Slope of the load line is minus 1 upon RC. Right? If the slope of the AC load line is minus 1 upon RC, then what is ICQ? ICQ definitely is VCQ divided by RC. It is from the simple equation of the triangles. This is 1 upon RC. The slope is 1 upon RC. That means for this triangle, the y upon x is minus 1 upon RC. And in that case, ICQ, this value has to be equal to VCQ by RC. This is one relation. But we still do not know the value of ICQ and VCQ. But this relation holds good. Also, from the DC load line equation, V is equal to VCQ, this voltage here, plus ICQ into RC plus RE. So VCQ is equal to VCC. This factor goes to the left-hand side, ICQ, RC plus RE. So now we put the value of VCQ from equation 2 in equation 1. This is the value of VCQ. Put this value in equation 1. If you do that, then ICQ is equal to the whole thing, VCC minus etc., divided by RC. Or cross multiply ICQ RC is equal to VCC minus ICQ RC minus ICQ RE. So this is ICQ RC. Take it to the left-hand side. Then you have on the left-hand side 2 ICQ RC. Right-hand side, you have 2 ICQ RC and ICQ RE also you take to the left-hand side. So this becomes equal to VCC. So what is ICQ? From here, ICQ is equal to VCC divided by 2RC plus RE. 2RC plus RE. So this is the value of ICQ. And this red equation I have shown, this is the equation that engineers use, because we have said earlier that RC plus RE is RDC and only RC is RAC. So this is actually RAC plus RDC. So ICQ is equal to VCC upon RAC plus RDC. Then we can find out VCEQ from this equation 1. So from this equation, VCEQ is equal to ICQ RC is equal to this value multiplied by RC here, and we divide both numerator and denominator by RC. Then finally it becomes, this is the equation theoretically we keep in our mind, but practically this is the equation is easy to remember. This is VCC upon 1 plus RDC by RAC. So these two red equations, they give you the value of ICQ and VCQ, right? So here I have found out the value of ICQ and VCQ. That means half of the design is complete. Next, more components are to be added. These are essential components, which makes this little bit, makes the amplifier a little bit clumsy looking, but we have no option. One is output coupling capacitor CO, which was not there. Why this? So that this DC current does not flow into the load. And what is a load? Load actually is the next stage of equipment. Your amplifier, it must be used by somebody for his equipment, electronic equipment, right? But you cannot send in DC current into that electronic equipment because its input, output, everything is designed for signal, right? So this capacitor will block the DC current going into the load. Next is the input coupling capacitor CI. Why we need this? So that the DC current from VCC does not go back into the signal source. Suppose this is amplifier you have designed and you have used signal from somebody, maybe from a mic, handheld mic, and maybe your output you are giving to a power amplifier. So from your amplifier should not go back into the mic, neither it should go into the power amplifier. So both sides there are two coupling or decoupling capacitors. Also the load. Now you cannot design an amplifier without taking care of the load. But how to do that? What is the input? Actually, this load RL is not a part of your amplifier. It is a part of the next stage of equipment. And RL is actually the input impedance of the next stage. And your amplifier without considering RL. And what happens? For the purpose of AC signal, RC and RL becomes in parallel. That is the danger, or that is the difficulty. Because I said earlier, I think you have learned it in your network theory classes also. So for all DC sources are practically short circuit for AC signal, for AC current. So when AC signal or signal current flows through this RC, it flows through the power supply and comes back to the ground. From here, through this and comes back to the ground. And also from here, it comes back to the ground. So RC and RL are in parallel. Since they're in parallel, so what happens? You have designed your bias point, etc., considering RC. But now if there is a RL in parallel with RC, obviously that bias point will be affected. So what you can do, this R, what you need, RL should be as high as possible with respect to RC, so that even when they are in parallel, it does not much alter the parallel combination value of RC and RL. Now, but RL cannot be chosen. It is somebody else's equipment. Ask them and know the value of RL, that is input impedance of their equipment. Know RL and then choose RC much lower than RL. Then you are at the same thing. If you choose RC first and you want a high RL, you cannot, people will not allow you. So what do? You ask what is the value of RL and then choose RC much lower than RL. And if nobody tells you what is the value of RL, then what do? You empirically choose for your design RL to be around 10 kilo, because for all practical purposes, all such electronic equipments, their input impedance is much more than 10 kilo. In fact, it is of the order of, sometimes it is the order of megohms. If it is a FET input amplifier, the input impedance is of the order of megohms. So if you choose 10 kilo, you are always in a safer side. So you design your amplifier for appropriate gain with a value of RL of, right? Now, an impedance in the path of VO, because output goes here, output goes out from here, right? So this creates an impedance in the path of the signal output. So CO should be much lower than RL. If RL is 10 kilo ohm, then impedance of this capacitor CO should be 1 kilo ohm or even less at your signal frequency, right? And CI also creates a path in the impedance, creates an impedance in the path of the signal. That means if it is very high, there will be a smaller signal current, right? So this, and there was a resistance RB here, right? So this value, impedance value of CI must be much lower than the equivalent, parallel equivalent resistance RB. And whenever we say lower or higher, you take 1:10 ratio. So these are the, finally, three new elements, two coupling capacitors and the load resistance, which comes into. And next we shall go to the actual design procedure. So far we have learned what are the events and not how to, I would say what are the conditions of, what are the mathematical or arithmetic equations to decide those values, right? And in our next lesson, we shall actually design an amplifier, right? But that is in the next lesson.